Today we study ESA9H, rotation matrix and trigonometric addition formulas. Let us consider the rotation transformation of vector A from to A prime by an angle of theta counterclockwise. This vector is on the xy plane, and we rotate this A, into A prime by an angle of theta counterclockwise. The rotation matrix is obtained like this because the unit vector E1 transforms into cosine theta sine theta, that is E1 prime, and the unit vector along the y-axis is transformed into minus sine theta cosine theta, that is E2 prime hat. As a result, Cartesian components A is A1 E1 hat, A2 E2 hat is transformed into A1 prime E1 hat, A2 prime E2 hat. We keep the original basis vectors, and the Cartesian components has been changed. If we fix the axis of rotation, in here we have an axis of rotation that is a z positive z-axis, then the multiplication of two rotation matrices is commutative. That means if I rotate by an angle of alpha first and then rotate another angle, beta, then the resultant rotation is the same as the single rotation by A alpha plus beta with the same axis of rotation. And this is identical to the rotation by an angle of beta first and then alpha. The resultant one is a single rotation by an angle of alpha plus beta. As a result, we can find the constraint. The rotation by an angle of beta first and then by alpha can be obtained by multiplying two rotation matrices. Explicit computation of this row, product of this row and column, will give cosine, cosine, sine, sine with negative sign. And this second row and first column multiplication will give sine, cosine, and cosine, sine. What about this? Cosine, sine, sine, cosine with both negative sign. And then the last element, two element, this can be obtained by multiplying this row and the second column. Minus sine, sine, plus cosine, cosine. We find that these diagonal elements are identical to each other, and because the product of two rotation matrices about the same axis of rotation is this, without computation, we can say that it is a cosine alpha plus beta, cosine alpha plus beta, and sine alpha plus beta, and minus sine alpha plus beta. That can be obtained by substituting alpha plus beta for the theta appearing in this rotation matrix. As a result, these two matrices are identical to each other. This relation will give the sum of cosine alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. Sine alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. So these are the trigonometric addition formulas. Let us consider a special case where alpha and beta are the same. Then our alpha plus beta becomes the same as theta, then it is a 2 theta. Therefore, the rotation matrix with the angle 2 theta is cosine 2 theta, sine 2 theta, minus sine 2 theta, cosine 2 theta. We can substitute alpha equals beta equals theta in this product. We find this is cosine squared, sine squared, and minus 2 sine cosine, and plus 2 sine cosine, and cosine squared minus sine squared. The identity leads to the constraint equation that cosine 2 theta is cosine squared minus sine squared. We can make use of, there's a typo, sine squared theta. Pythagoras' theorem states that the cosine squared plus the sine squared equals 1. Therefore, it can be cosine 2 theta can always be expressed in terms of sine theta or cosine theta. So the result is 1 minus 2 sine squared theta or 2 cosine squared minus 1. In a similar manner, I can obtain the r3 theta that can be obtained by cubic r or r multiplied by r squared. In any case, we can obtain at the final stage, we can obtain the expression in terms of only cosine theta or cosine theta squared, cosine theta, the powers of cosines. So multiples, rotation matrix with the multiples of a finite angle can always be expressed as a polynomial of cosine theta and sine theta. It is a very, very important. Using this, we can extend our knowledge about the value of the rotation matrix or sinusoidal function at larger angle, magnify the argument, and express that argument in terms of a value that is, for example, the sine theta is very small. It approaches the theta. So using this method recursively, we can find the value of sine theta with a finite value of theta in terms of small values. We can make use of reduce to carry out this tedious calculation with ease. Why don't we make use of R equals matrix this? Wait a second, we can run the program immediately. We run reduce. And copy the program. Okay. So we have defined the rotation matrix, cosine minus sine, sine cosine. This is a first row, and this is a second row. R2 then means R squared. This is R multiplied by R. So first one, we have R, that is cosine sine minus sine cosine. Okay? The second one, I have R squared, that is a cosine squared minus sine squared, cosine minus sine squared. All right. What about this? This is I have simplified this, and I'd like to check if I have made any the typographic errors. So we can subtract this simplified version out of original r squared. So the final result is a 0. That means I have computed in a correct way. What about r cubed? Just the direct computation of r multiplied by r squared will lead to this computation. And I have simplified this expression, subtracted to find the 0 matrices. So, therefore, I have a verified expression that is given in this lecture note. We can make use of the following relation recursively to find cosine n theta and sine n theta. So this recursive relation is like this. This is based on the fact if I fix the axis of rotation, the double rotation will lead to a single rotation with the sum of the two rotation angles. So this one is completely expressed in terms of cosine n plus 1 theta and the sine n plus 1 theta. And this one, right-hand side, is completely expressed in terms of cosine theta and cosine n theta. If I down the scale, then cosine n theta, it can be expressed in terms of cosine theta and cosine n minus 1 theta. If I keep this one going again and again, then we will reach the point everything is expressed in terms of cosine theta and sine theta. And any powers of sine, even powers of sine squared, sine, will be expressed in terms of cosine theta by making use of the Pythagoras theorem. Cosine squared plus sine squared equals 1. In this manner, we can simplify multiples of a finite angle, that the sine function of an angle that is a multiple of a finite angle theta can always be expressed in terms of cosine theta and sine theta. The Chebyshev polynomial of the second kind is defined in such a manner, and the explicit form of Chebyshev polynomial can be obtained by repeating this calculation. And even though it is tedious, it is very, very straightforward to find the result. An explicit computation leads to the explicit values for the Chebyshev polynomial in powers of cosine theta. We recall that a squared is invariant under rotational transformation because it is a scalar product, and in general, any scalar product is invariant under rotation. The rotation matrix is like that. If I rotate a vector into a prime with the angle about the z-axis, the final result is like that. In a similar manner, the b prime that is obtained by rotating vector b is like that. We'd like to compute the scalar product of the two vectors before the rotation and after the rotation. This is before the rotation. Before the rotation, it can be expressed as a product of the row vector representing B and the column vector representing A. By the way, in the prime case is A prime is rotation matrix multiplied by A. B prime is rotation matrix multiplied by B. However, if I want to compute the scalar product, I have to let this A, either A or B, and as a column vector, and I have to make a transform into a row vector. That is to take the transpose. We recall that the transpose of a vector is this, and this column vector B prime can be expressed as a product of a rotation matrix and original vector B. We recall that the transpose of two matrices is a product of the two transpose matrices after being exchanged. So this one, right hand side, this one should be moved to the left, and we have to take the transpose. We have to move this one to the right, and then we have to take the transpose. As a result, this one becomes a row vector, and this one becomes a transpose. And because the rotation matrix is orthogonal, transpose is nothing but the inverse matrix, the opposite direction, rotation by an opposite direction. As a result, B prime and the scalar product of B prime and A prime can be expressed as the original vector's scalar product before rotation, and in the middle, what we find is just unit matrix, identity matrix that does not transform anything. As a result, because the orthogonal matrix, the rotation matrix is an orthogonal matrix, the scalar product of two vectors before the rotation and after the rotation, they are invariant. This is the consequence of the fact that rotation matrix is orthogonal. That is, the transpose is identical to the inverse matrix. That's it for today. Thank you.